Okay, good morning, everyone, and thank you for joining us for today's webinar on synchronous and cogged fan belts. We'll get started shortly, but before we do so, my name is Andrea Silvestri, and I wanted to go over a few webinar logistics. So today's webinar is based on research that NREL completed in 2014, and the full report as well as the 4-page findings and the 1-page infographic are available on the GSA website at gsa.gov/GPG. You can also find a list of additional savings there as well, additional resources there. And this is one webinar in a series. Our upcoming webinars are in September. On September 14th, we'll be hosting a webinar on catalyst-based non-chemical water treatment. And this is a unique technology that relies on a pipe with a helical insert to prevent calcite buildup. And it was found to be an effective treatment for facilities with hard water and to have immediate payback when compared to chemical systems. In October, we'll be hosting a webinar on 2 next-generation chillers that GPG has assessed, the variable speed magnetic bearing chiller and the variable speed screw chiller. Both these chillers are 35% more efficient than FEMP-designated chillers, and they were both shown to have incremental payback under 5 years. In November, our webinar will discuss findings from multiple GPG assessments of electrochromic windows. And electrochromic windows respond in real time to weather and user preferences to change the window tint. And the recent assessments are focusing on occupant satisfaction in 2 buildings, one in Portland, Oregon, and one in Sacramento, California. GPG webinars now offer continuing education credits, and you can, through the American Institute of Architects. And to receive, if you wish to receive credit, you can complete the post-webinar survey that will be mailed to you shortly upon completion of today's webinar, or you can contact Michael Hobson at his email address. The broadcast today is set to listen only, but you can submit questions here on the right side of your screen. And you don't need to wait until the Q&A session at the end of today's webinar to submit questions. In fact, we encourage you to submit those questions well in advance. And now let's get started with the webinar. Michael will be facilitating today's presentation.
Thank you, Andrea. Next slide. Today's webinar will include a brief overview of GPG by Kevin Powell. After this overview, Dylan Cutler, the National Renewable Energy Laboratory and the primary investigator for the GPG assessment of synchronous and cogged fan belts at the Byron Rogers Federal Courthouse in Denver, will summarize the research results. Dylan's presentation will be followed by on-the-ground feedback from Michael Higdon in Denver. Also, it will include some feedback by John Teagan in Region 3. We'll end the webinar with an interactive Q&A session. And then Andrea, is Kevin here?
That's a good question. We're checking on Kevin's audio right now. We'll move to the next slide. And I think, Mike, it's probably a good idea if you want to present these slides for Kevin. Because we do not hear Kevin right now. Although, let's see. Kevin, can we hear you now?
I don't know. Can you hear me now?
We can hear you now. Okay, great. Here you are. Welcome.
Okay. Thank you. Thank you. Okay, so next slide. So just a few words about our program. I think many of you are familiar with it. A few of you may not be. But the key point of why we do what we do at GSA with the GSA Proving Ground is to enable our agency to make the best investment decisions in technologies that really can deliver performance in the real-world conditions of our buildings. Next slide. The key thing, and you'll hear that on this this webinar, and you'll hear this on upcoming ones, is not that there's a lack of innovation out there, and innovation can range from really incredible material science, really at the cutting edge, to something as simple as we're going to hear in this webinar as just an improved fan belt. But the key thing and the barrier that we all face really is that while there's a good pipeline of innovation, the fact is we operate buildings full of expensive equipment and we operate them for the long term. And the challenge is that without assurance that what you're going to be putting in actually really will deliver, there's a great tendency to play it safe and to put in what's worked before. So what GPG is all about is providing this kind of forum where we can say we tried this technology out in the real world of our buildings and we observed real savings from this technology's performance, and operators like it or find it acceptable to the degree that it would be facing tenants. In this case, it isn't, but the tenant would accept it, that there's good payback, and that to the degree there's a cybersecurity issue, that that has been worked out. And if you just look at this by, our previous commissioner described GPG as in GSA's enlightened, selfish interest. And the selfish part of that is we want these innovative technologies to come to market, those that really prove out and deliver, so that we can buy them at an attractive price, and then, of course, have the kind of real-world performance in our buildings that allows us to have buildings that perform so much better than the typical commercial building. So next slide. For those of you who are wondering how does the technology get into the GPG, we hold an RFI every fall, and I've got great news for everybody on the phone. This year, we were wondering if we were going to have sufficient funding to move that forward. It looks like we will. So the RFI will open. If you follow us on gsa.gov/GPG, you'll find more information. Should be out in early October. That's our way of identifying promising technologies at the edge of commercialization. People submit them to us. We then go through a down select process, pick the best of the best, pilot those at locations within GSA's portfolio that represent essentially an acid test, a challenging set of conditions for this technology to deliver in. We work with DOE National Labs to do these evaluations. DOE National Labs are not only world experts in how to do these kinds of evaluations, but they obviously are truly independent third parties that don't have really any skin in the game. And lastly, the whole point of this is not to create a series of reports that sit on a shelf somewhere, but really to identify those technologies that really have the greatest potential impact to help GSA with energy reduction and with cost reduction. Next slide. That is the cue to turn it over to Dylan.
Hey, thanks, Kevin. All right, so next slide. So I'll be just discussing the kind of technical portion, the analysis that we did on these cogged and synchronous fan belts, and some results, and that'll be followed up, like Mike had said, by some on-the-ground feedback. So this is the report. It's available on the website where Andrea indicated. Next slide. So this is basically the technology that we tested. Like Kevin said, it's not real, snazzy per se, or a whole new breed of technologies, but it's a more of an incremental improvement on something that's used in all of our buildings on a day-to-day basis, and therefore can actually pretty quickly deliver some modest but relevant cost savings and energy savings. So on the left, you've got your standard V-belt, and these are you know what connects a motor to a fan typically to drive that fan. And what we tested were both the Cogged V-belts, which are in the center, and those are very, very similar. They'll slot into essentially the exact same place that a standard V-belt would, but they reduce bending friction, bending resistance and friction. And so that's where they kind of deliver their savings. The next one over, even though it looks quite similar, the synchronous-drive belt, is actually a little bit more of a step change in the technology. This one, actually those teeth fit into new sheaves. So you take off the sheaves on the fan and the motor and put in new ones that have slots. It's almost like a bike chain. You can think of it that way, where they actually sink in and lock. And so that reduces belt slippage and friction again, providing savings. Next slide. This is just kind of scoping the opportunity for savings here. Approximately 12% of electricity in buildings goes to ventilation, and then there's additional, fans in cooling towers and other locations in certain buildings. And the claim is, that these are 2 to 5% more efficient than standard V-belts, the Cogged or the synchronous, and that bore out in our analysis. Next slide. This is where we tested the technology in the Byron Rogers Federal Courthouse in Denver. And we tested them both on a constant volume fan and a variable air volume fan, or a fan equipped with a variable frequency drive. So a fan that can change its speed via power electronics. Next slide. So this was the test plan. Essentially, what we did here was for both the constant volume and the VFD equipped fan, we tested them with original standard V-belts to obtain a baseline. So that's kind of what would have happened if no intervention had occurred. That's the energy consumption. And then we swapped out those fan belts for the Cogged and then the synchronous. We were measuring real and apparent power consumption and looked at fan speed, motor speed, and even sound level in the penthouse where the fans were located. And then essentially had to do some normalization of the power consumption for fan speed and air density changes, because when we do the baseline test with the standard V-belts, as soon as you change that for the Cogged or the synchronous belts, if the fan is actually moving at a different speed, that will result in different power consumption in a pretty drastic way. A technical equation called the fan affinity laws, which say that power varies with the cube of the fan speed. And so we really need to normalize out the fan speed. And then there's also, sorry, is anyone else getting that feedback?
I am too.
Yes, I'm also getting that feedback. Yep.
Okay. Sorry, maybe it just went away.
Yeah, it did.
Okay. All right, jump back in. So we normalized for fan speed, and then we also normalized for the VFD fan. That was pulling in outside air, and so we had to normalize for the air density because it takes more force to move denser air, or more power. So that was kind of the process, swapping out, testing. It was short-term monitoring of power consumption. For the VFD, we put the VFD drive into manual and stepped it through its different stages, and you'll see that in the results so that we could monitor kind of percent savings at different fan speeds. Next slide. So this is just kind of a note on the installation and some O&M considerations before we jump into the results. So what you're looking at in the pictures here, this is the constant volume fan that we tested. It was an exhaust fan. And so originally, in the top, you see those two standard V-belts. If you can kind of see it by looking at the lower sheave on the motor. There's two slots where those V-belts are tracking. The bottom picture shows it after the swap out for synchronous. And there you can see the new sheave with the kind of teeth in it, or slots, where the synchronous belt connects. And so one thing to note here is that the synchronous drive belt replaces two standard V-belts on this fan. It also replaced 4 belts on the VFD fan. And so that is one thing that drives some lower O&M and lower recurring costs potentially for these synchronous drive belts, are that you're replacing less belts. Also, you don't have to do the tensioning. I think often you'll do kind of quarterly or biannual tensioning of V-belts, the standard ones, because they kind of stretch out and you tighten them back up. The synchronous drive belts don't have that consideration. The cogged belts, the O&M is pretty much equivalent to standard V-belts. Next slide. Oh, Andrew, can you go back up? I just missed one point on that one. Can you go back up one slide? Yeah, thank you. So the torque on the constant volume fans, you can put in something called a soft start, but if you don't have that, and when these kick on, they kick on with a high power draw, and that initial torque can cause problems with synchronous belts, and we'll get to that in kind of lessons learned at the end. All right, next slide. Okay, so this is the fan energy savings that we saw on the fan with the VFD drive. And again, these are weather adjusted and fan speed normalized. And so the table essentially has a row for each VFD frequency that we tested at, and then the actual savings in watts for both the cogged and then the synchronous belts, and then the percent savings that resulted in. And you can see that the synchronous belts range from about 2 to 20% power reduction, depending on what speed you're at, whereas the cogged range more from 1 to 9%. If you look at kind of where the fan will be operating most of the time, maybe it isn't all the way down at 15 hertz. That's a pretty low speed. You're going to see kind of this maybe 2 to 5% savings for the synchronous belts, and maybe 1 to 3 or 4 for the cogged. But significant and pretty strong results. Next slide. So this was kind of the life cycle cost analysis that we did, and there's just a couple of things I think worth pointing out here. These were, the first row is kind of the initial cost for the standard V-belts, buying 4 of them. A little bit more expensive for the cogged V-belts, but really not much more expensive at all. The initial cost for the synchronous drive belt is drastically more expensive because you're actually swapping out those sheaves and doing a real heavier touch retrofit. The replacement costs are actually cheaper with the synchronous drive belt because you're purchasing 1 belt in this case, an expensive belt, albeit, but versus 4. And then the O&M costs are lower. In this case, we considered that all of the belts had the same lifespan of 3 years. The manufacturers claim that the synchronous drive belts have longer life, and I think some of the results that Michael Higdon will talk to, that's borne out in this case. But we assumed equal life because we didn't have any data around that other than the manufacturer's claim. And so you see kind of the life cycle cost analysis in the bottom row. This is assuming 9 years, so 3 replacements of each belt. And so it bears out that they're both cogged and synchronous are life cycle cost effective, with synchronous being the best choice in this case. And as you go out further and further, this will only get more kind of a bigger difference, because each time you do a replacement, you're actually saving money, and your initial cost difference is getting kind of minimized. So next slide. So this is the synchronous belt on the constant volume fan. So a couple of things to note here. The fan energy consumption actually increased in this case for the synchronous belt. And so this gets to kind of some recommendations and a kind of key point that I sort of touched on earlier. But you'll see that in the first columns here, you'll see an increase in fan speed and an increase in power consumption. And so where that comes from is that when the synchronous belt was swapped onto that fan, it actually increased the RPM and therefore the power consumption. And that has to do with sizing of the belt relative to the fan, a number of different kind of variables that can impact whether the fan speed goes up. But with a constant speed fan, you really can't do anything about that once it's installed. With the variable speed drive, that when it's not in manual, when it's in an automatic mode, usually set to kind of maintain a duct static pressure set point or something like that, it will ramp to kind of meet that set point, and therefore this isn't as much of a concern. But in the constant volume fan, an increase in fan speed just because of the sizing of the belts, you can't really get away from that. What we did do was, if you normalize the third column here, if you normalize for that fan speed and assume that you could have hit the same fan speed with the new belts, we actually do see a saving, about a 2% improvement in efficiency for the synchronous belt. So that's just something to note when you're kind of doing these installs, is you need to have them sized right so you don't end up actually just increasing fan speed, which overcomes the savings you would have had from reduced slippage and friction. Next slide. So this was kind of an analysis that looked at varying electric rates and fan run times, because the couple of fans that we looked at, the economic analysis that we showed prior, that's just for that building and that amount of runtime for that fan. And so we kind of wanted to look at those variables a little bit. You see at increasing electric rates, the net present value of the synchronous drive belts, which is in green, overcomes the Cogged pretty quickly. As soon as you get over about 3 cents a kilowatt hour for your electric rate, you're going to get more return from the synchronous belt. And then, the same picture with higher run times as well. So that's kind of a little bit of a sensitivity on electricity rate and fan runtime. And they're both cost effective at very low electricity rates and pretty modest hour per day runtime in this analysis. Next slide. So here's some kind of just lessons learned. We kind of hit on that first one already. Ensure correct size. So we need an experienced installer to measure the pre-existing diameter, belt length, and shaft speeds. And so that's pretty important to get an experienced installer, especially really for the synchronous belts. The cogged ones, they're basically just, you stock those instead of standard V-belts, and you got to get the same size, but they're pretty much just a one-for-one swap. Considering the range of mobility in the motor mount, so just because you're dealing with different sheaves and a different size belt in this case, you need to make sure that you can kind of move the motor enough to kind of whatever size fits roughly that fan scenario, you need to be able to move it a little bit to kind of tune that correctly. And then if you are looking at using synchronous belts on constant volume fans, considering a soft start, because that initial torque is pretty loud and can cause kind of tooth jump and wear on the belt. Next slide. So these are kind of the final slide for me, I think. Some takeaways for VFD fans. These synchronous belts really did show savings at all ranges of fan operation, and are recommended. They're life cycle cost effective as far as we've seen in this analysis. For constant volume fans, we recommended Cogged V-belts as the best solution. They have a moderate savings, and they're really not that much more expensive. It's a very small incremental cost to stock those instead of standard V-belts. And as we said, there is this kind of risk for increasing fan speed or these high torque starts on constant volume fans. And then while we were doing the sound measurements, there was no significant change in the sound levels generated by different belt operations. I think Michael may have seen some increase in noise in the penthouse with that constant volume synchronous belt since in ongoing operations, but we measured no differential. I think that's the last slide. Sorry, one more. So standard V-belts at the end of life, look at replacing, as I said, with Cogged on all constant volume fans, and consider synchronous for VFD fans. And again, this is the recommendation is really when fans have high operating hours. That's going to be a big opportunity, just because you'll get more kilowatt-hour savings to offset the initial cost. And then really in new construction and major renovation, these synchronous drives should be spec'd from the get-go. Next slide. That's for Michael.
Yes, Michael Higgins here, equipment specialist in the Region 8 Denver Byron Rogers complex is where I work. Go to the next slide here, and let's see what we're looking at here. Okay, the first fan that we're speaking of here is the Byron Rogers parking garage ventilation, which is 40 horsepower, and that it's designed with the 1185 RPM was reduced down to about 67% of the initial design, because the emissions of the vehicles of today compared to the vehicles that were here back in the 60s is much more controlled. So we were able to slow down the ventilation, and in turn, when the synchronous belt was attached to the system, we were able to slow down the whole system from the VFD that was installed for this unit. And in turn, it has revealed that this belt system has lived a very long life, and it looks as though that it has quite a few hours to go before it will need any replacement at all. The reduction on the wear and tear of the motor and the fan bearings are much longer now, which is a good result. The noise level for this unit is very low. You can hardly tell the system is even running until you open up the air handler to find out it's actually running according to what is on the VFD. To the next question, next slide. Okay, this one here is the same ventilation that was being spoke about on the previous speaker. This unit here It has a 10 horsepower, and it spins pretty fast at 1760 RPM. This unit doesn't have a VFD, so it does have a little, it has a hard start. And in the repetitive hard starts of becoming occupied and non-occupied modes in the VAS, it does jar the system a little bit. And over time, it has created some vibrations because the hard start is now wearing away on the belt, which was the original belt when it was installed. It's starting to wear away on the teeth of the belt. The shivs are fine. They're not wearing away yet. But it has brought it off a little bit off center. And as you can see in this slide where the belt's riding on one side of the shiv. And that, I think, is what has increased the little noise level. So it has increased a little bit. However, I believe that if this unit did have a VFD controlling the startup of the unit to where it was a soft start, and maybe even slow it down, because since it did increase the air volume, I believe that the system could be slowed down. I believe that that belt wouldn't show any wear and tear at all if it had the VFD installed in the beginning of the belt installation. So unfortunately, it's coming to the close to the end of its life span on the belt. And I'm encouraging the GSA building management to do a project to place the VFD on this unit to slow it down and get a better control. And I think once they put the new belt on, I believe it will run for quite a few years, just like this one has, but even longer. Next slide, please. Okay, on these charts that are attached to this unit is before and after energy usage, but I was not involved with this part. So trying to read these graphs, I believe is going to be up to the viewer. But maybe Andrew Olson, who I believe is on, he might be able to answer some questions on these graphs. Next slide. Okay, so this is going to be turned over to John Kazin.
Okay. My name is John Teagan from Region 3. Briefly, if you can, Andrea, go to the next one. I only have one slide, so try not to belabor this too much. Region 3, as part of our ESA requirements, when we had our initial building studies done, used NREL to perform those studies. And in the initial NREL reports, of course, Dylan works for NREL, they recommended replacing our standard V-belts with the Cogged belts. Region 3's O&M vendors really embraced these findings when we sat down and went over the reports. And they switched to the Cogged belts when performing their PMs really at the earliest feasible chance they had to swap out the existing V-belts with the Cogged belts. Pretty much right now, I won't say you couldn't walk into a Region 3 building and find a standard V-belt, but they're pretty difficult to find in a Region 3's inventory. If you see that the O&M has stocked spare belts, they're all Cogged belts now. All this work in Region 3 was done as part of the O&M contract. There was, no money outlay or a specific project where we went to our O&Ms and said, hey, we want to change all these belts out. So it was just kind of a, it just spread out on its own. And this is one, it might be the only green proving ground or GSA proving ground project where you don't really have to run a project to do it. It's not customer facing. To the best of my knowledge, we've never received a single complaint that we changed from one belt to the other. It's probably the easiest one to do. In Region 3, we consider this a best practice. Our O&Ms consider it a best practice. They point to it as them, implementing best practices as they come along. And they're operating the equipment in the most energy efficient way possible, and it's been very well received. Absolutely no pushback from anybody, to the best of my knowledge, in Region 3. And like I say, you would have a pretty difficult time walking through a Region 3 building and finding a regular V-belt. We have used some of the synchronous belts, but as specified by projects and when things were installed. But just in general, we for several years now have been using the Cogged belts with great success. And that's my slide.
Thanks, John. And before we move on, we'll move next to Q&A. So if you have any questions, please enter them now. So as John said, we've had a lot of uptake of the Cogged V-belts in GSA among the regions. Not as much deployment of the synchronous-drive belts. And that might be interesting fodder for questions if people want to talk about that. And Mike will move on to Q&A now.
Okay, thank you. Let me go to that. Shad asked, why such a drastic, so Dylan, this is for you probably, why such a drastic difference from 20 to 15 hertz? And this is on your way at the top slide, where we were looking at the energy savings between, standard cogged and synchronous.
Yeah, it's a great question. I think this gets a little bit into the weeds, but I think that the main explanation here is that, and a bit of the reason why you're seeing increased savings at these low VFD speeds is because they also correspond with lower power factor, and that's one of the places where you're actually getting some real power savings, is that there's actually a reduction in power factor, which I know in general we don't think of that as a very good thing. That's one of the things that can result from these synchronous belts, and this is detailed in the report. But that reduction in power factor is slightly larger at lower VFD speeds, and so savings go up.
Mike?
Yes?
Mike?
Yes.
Can you hear me?
Yes.
Hi, this is Ronald Whitley at OFM in Central Office. I just had one question, and that is, this technology, in terms of, at least in the automotive industry, has been around for the last 20 years, which has worked very well, and you're right, the belts are very long-lasting. But one way they got around the torque issue was putting an idler pulley against the belt that was spring-loaded to take up the tension of torque. Has anything like that been considered for this particular effort?
Not that I'm aware of, but I'll ask John and Michael if you're aware of anything like, have you utilized that strategy?
Okay.
Nothing in Region 3 that we've ever tried with that. We didn't really do the NREL study with them. So, like I said, we just had good success just putting them where the V-belts were, and we marched on happily ever after.
Michael, any?
Michael, we haven't applied any of that belt tensioning process over here at the courthouse at all. But I do believe that that would probably help on the teeth of the shiv and keeping the belt in the groove on the hard start. I do think that would probably help. Yeah.
And not to mention the fact that it certainly reduces the wear on the belt itself.
Okay, thanks, Ron.
Thank
Joe
you.
asked, does installation cost comparison include cost of changing sheaves from V-belt to cogged or synchronous? And maybe clarify that with the cogged you don't need to change sheaves. But
Yeah, yes it does. So yeah, the cost includes changing sheaves from V-belt to synchronous. From V-belt to Cogged, you don't need to change anything except the belt. But yes, for the initial cost, you see like that $1,280 for initial cost on the synchronous belt. That's both the belt and the new sheaves and labor.
Okay, thanks.
I have one of the real quick question on in terms of the analysis that NREL did on this particular item. Was there any type of difficulty factor placed? I mean, it sounds like to me this technology in our buildings would really be beneficial in those areas of where we have equipment that is so hard to get access to, or equipment that would be absolutely essential to, you know, mission critical type services that we provide to our tenants. So I was just wondering if there was any type of factor that might apply to that as well, because that would certainly be a huge savings in man hours, as well as in the idea of making sure that we have equipment that operates without any type of failure rate.
Yeah, so we didn't kind of add a weighting factor for kind of criticality of equipment. I think you make a good point. You know, if this has shown to be a pretty dependable technology, maybe it is kind of that's an added benefit. What we did do was, you can see here the kind of reduced O&M cost for the synchronous drive belt. You know, that reflects less touch from the O&M staff. So you do, you know, after that initial swap out of the sheaves, these are like immediate payback. It's a cheaper belt than buying 4 belts, and you've got reduced annual O&M. So you've got kind of and you've got energy savings. So you've got a number of things working for you as soon as you kind of overcome that initial cost. But no, we didn't add a kind of criticality factor.
Okay, thanks. And then Mike asked, what was the kilowatt cost for this slide, number 19, I guess, slide 19?
For which?
I think it might be slide 20, the slide we're looking at.
Okay.
Yeah.
And Andrew Olson, I don't know if you can tell us what, you know, Region 8 rates are, but it's what, 10, 11 cents a kilowatt hour?
Yeah. I think, okay, I'm pulled up the report. 8.4 cents per kilowatt hour was the cost of energy. So every kilowatt hour saved, you save 8.4 cents.
Great, thanks.
If I could add one more additional comment, and I promise after this I'll shut up. One of the other items that certainly is beneficial to this type of technology is the fact it's the reduction in heat load associated with belt slippage. And therefore your motors, you know, should last a lot longer, and the bearing surfaces on your air handlers should last a lot longer too as well, because the heat is minimal in those areas.
Okay, thanks, Ron. And one additional question. Manny asked, are there published adjustment factors for ensuring the same fan speeds?
Yeah, that's a good question. This gets into kind of choosing a good installer. I think there is a mapping from, like, you know, you have X belt of this diameter and this length. Here's the equivalent synchronous belt that you should purchase and put in. But I guess it's not just that simple. You know, it's kind of moving the motor mount to ensure kind of the correct tensioning and kind of it's I think it's, while there is that mapping, I think that having a vendor that's done this before and knows the kind of nuances and kind of in telling them that you're concerned about fan speed, you know, those are all things that would be recommended in purchase and installation.
Thanks, Dylan. Andrea, I think that's it for our questions.
Thank you. So let's see. Oh, we have one more question there, Mike, and then we'll.
Shad asked, was there any premature thrust bearing failures reported? Or was this just at Byron Rogers?
I can answer that, and the answer is no. In fact, the pressure that's on these bearings is less with the synchronous belt than it is with the, for instance, the garage ventilation with the 40 horsepower had 4 belts of just the V-belt type, which is a much greater pressure on the bearings than the one single synchronous belt. So and plus that one has the VFD, which is the soft start as well, and so the pressure is less and less torque on those bearings. Now the smaller unit, the 10 horsepower unit, I think that it's a fairly small system, so I don't think there's that much torque on that system to begin with on the startup compared to the two-fan V-belts that it had before, which had a lot more pressure on them than the synchronous belt. So I would say that the torque on all the bearings, on the motor bearings and the fan bearings on the pulley side, are both greatly reduced because the belt has less tension on it than the V-belt type. I hope that answers that.
And hey, Mike, sorry to interject. I have one more thought kind of back on Shad's question on the energy, the percent energy savings at those low speeds. I think another factor that goes in there is that there is more slippage with standard V-belts when you get down to those low speeds. And so when you take that away, you get even better kind of savings from that aspect.
Gotcha. Okay, thanks. Any more questions? I don't see any.
I see maybe one being typed, but meanwhile, so everyone should receive a survey shortly in your email, and by completing that survey, you can request continuing education credit. And if you don't receive the email with the survey, please reach out to Michael Hobson. And so thank you, everyone, for presenting and for participating in today's webinar.
Yes, thank you. Bye, everyone.
Thank you.
Bye-bye.
Thanks.